好，那现在我们来看一下这个 Taylor series 的应用。那这里谈到的是所谓的 Taylor polynomials。Taylor polynomials 其实呢，指的是我们砍掉一半的那个 Taylor series. Alright, so down here we're looking at the applications of Taylor series, or in fact that of Taylor polynomials. What we call polynomial is this polynomial, right? So it is the Taylor series that has been truncated. This is a Taylor polynomial. Right? This is a polynomial. And we see how it's going to be applied in physics. OK, 那就是这个多项式，因为 Taylor series 砍掉了之后呢，剩下的其实是有限的项次，那这些就是一个多项式。那 Taylor 多项式呢，常常在物理里面应用。那这个是因为通常我们在研究一个物理问题的时候呢，通常都会碰到一些函数，这些函数可以是复杂或者简单，但是通常又有不同的这个变数，甚至是呢它是一个非线性的函数。那在这个 Taylor series 的应用方面呢，那物理学家通常就拿一个 Taylor polynomial 作为一个函数的近似函数。Right, so what we use Taylor polynomials for is in fact as an approximation to a function that we encounter in physics. 那接下来 Taylor's inequality 呢，又可以用来就判断一下这个近似函数呢到底有多准确。So the Taylor polynomial, we would also like to know its accuracy as an approximation. So for that, we can analyze its accuracy using Taylor's inequality. So in the next example, we're going to look at a problem in special relativity. OK, 那接下来我们看一个关于特别相对论的一个例子。那根据爱因斯坦的特别相对论，那一个在以 v 速度前进的物体，它的质量呢，其实是由这个式子而定。式子上面的 m0 就是等于是这个质点呢，在0速度下的这个速度的质量 ，right? So m0 is the mass of the object when its velocity is 0, right? So if we set v equals 0, then m would be equal to m0 over 1 minus 0 here, and that is m0. So we can view this, in fact, we can view m now as a function of v. 所以在这里我们的这个质点的这个质量呢，其实它是跟这个一个速度形成一个关系，我们可以把它看成是速度的函数。那另外呢，就是说这个物体的这个动能呢，就是所谓的 mc² 减去 m0c²，这个可以把它看成是静止的能量。物体的质量等于静止质量时候的能量。那它确实的动能呢，是等于 mc 平方减去这个静止的能量 ，right? So, in relativity, the kinetic energy of the object is in fact the difference between its total energy given by mc² minus its energy at rest. Now remember this m0 is the mass of the object at rest. So when we take away the energy at rest, what we have left, we call that k. This is the kinetic energy of the object. 那现在我们来看这个例子，就是说我们要探讨的时候，当 v 很小的时候，当速度是非常的小，相对于这个光速 c， 相对于光速 c 很小的时候呢，我们是要探讨是否这个所谓的动能呢，会回到我们在典型物理里面，牛顿物理里面所碰到的那一个动能啊。记得在牛顿物理里面呢，那个动能是1/2 m0v²，m0 是静止啊，就是非相对质量啊，非相对质量是 classical 啊，这个静止物体的这个质量，也是速度非常小的物体的质量。So the first problem we are going to look at is when v is very small, the velocity of the object is very small compared with c being the velocity of the speed of light, right? What is the speed of light? So if the object is moving very, very slowly compared to light, then we would like to know if the expression for the kinetic energy recovers that we have seen in Newtonian physics. So remember, in Newtonian physics, that's the classical physics that you learn in high school, the kinetic energy is 1/2 times mass of an object at rest times square of its velocity. So we want to recover this, see how we can recover this equation. 那接下来呢，就是用这个 Taylor's inequality 呢来判断呢这个这个式子跟上一个式子的误差。如果假设我们用这个式子作为速度的一个近似的函数，那它跟原始的相对这个相对的这个动能差有多大 ？OK， 那现在我们来做这个第一题。首先，我们把这个相对动能，下面这个相对动能呢，先把它的式子给写开来。那记得这个 mc² 减 m0 square m 呢，我们就代入刚才那个式子，不要忘了这个 m 是等于这个函数。所以当我们把 m 代入到这个 k 的式子的时候，我们得到的是最右边的这个式子。那现在我们就要来探讨，当 v 很小的时候，我们能够做什么样子的一个近似的表达法 ？Right. So now we have substituted the expression for the relativity mass m into the expression of k, and after arranging the terms, we get this expression here on the right. Now we would like to know if v is very small. If v is very small, can we find an approximation for this expression? 就是 v 非常小 ，v 非常小的时候，也就是说这个 v over c 是非常小于1的 ，right? So we are looking at a case when the ratio between v and c is very, very small compared to 1. Now, since we are looking at such a problem, very naturally we think about the Taylor series as an approximation. So let's look at this expression. Let me just rearrange it so that it's clearer. We have in factor m0 times c squared, and then in the bracket, this is in fact 1 over square root of whatever is in the parentheses. So let me just write it out. In fact, 1 over the square root of 1 minus v squared over c squared, and then outside we have a minus 1. Close bracket. Alright, 那我整理一下呢，这个 k 的式子呢，就看得出是一个根号分之一的这个式。那现在我们来探讨一下这个函数 f of x 等于1减 x 的根号分之一 ，right？ 那要是 x 非常小的话，那我们就用它的 Taylor polynomial。We approximate f of x with its Taylor polynomial. Right? 那首先我们就要写出它的 Taylor series. In order to do this, we must first write out the Taylor series. So let's do what we usually do to get the Taylor series. For n equals 0, f of x is just f of x. Okay, I'm just repeating the function. For n equals 1, we are going to differentiate f to get f prime of x. Now this, we will need the chain rule. Okay, 那在做这个微分的时候，我们就用 chain rule. 我们的 chain rule 是要做什么？是 d du of 1 over u， 因为我要把 u 取代1减 x， 再乘上 du dx， right？ 那 u 根号分之一的微分，这个就是2负2分之一乘上u 的3分之2次 ，right？ So the derivative of 1 over u square root of u is minus half times 1 over u over 2, okay, u to the power of 3 over 2. Then du dx is just 1, right? Forget du dx. So if I reorganize this, and I put back what u is, okay, 整理一下，再把 u 带回去，这个就是我的 f prime of x. 接下来 n 等于2，我要取 f 的第二次微分 ，so I need the second derivative of f. So I need to make a differentiate this one. Now I already have a 1/2 in front, and I'm going to use the chain rule again, but this time the chain rule applies to du of 1 over u to the power of 3 over 2. Alright, 所以现在是 u 跟2/3次分之一的微分，但是不要忘了 u 还是取代1 minus x， 所以接下来还要乘上 du dx. Right? After this, I just differentiate the fraction 1 over u to the power of 3 over 2, and that gives me minus 3 over 2 times u to the power of 5 over 2 times du dx. Du dx is always minus 1. So after organizing the terms, I get 3/4 of 1 minus x. Oops, this is power of 5 over 2. Here. Let's do one more term. Right, so I'm going to skip the so-called chain rule. I'm going to do it directly. 所以 chain rule 我就直接做，不用再详细的写。Alright, 所以这个 chain rule 直接得到的就是这个 chain rule 得到的结果，微分的结果是负5/2乘上-1 over 1 minus x 的7/7. Right? So this is the result of my chain rule. I get 15 over 8, 1 over 1 minus x to the power of 7 over 2. So now we have to decide where are we going to write the Taylor polynomial. 那这个 Taylor series 我们到底要写在哪一个位置？记得我们是要写在 a 等于什么地方嘛，对吧？When the center, okay, this we need the center of the Taylor series. 那既然我们在考虑这个since we consider x very small, 我们既然在考虑 x 很小，小于1及小于1，那当然我们就选择 center 呢，就是 a 等于0，就是把这个 Taylor series 写在 x 等于0的位置。Since we are considering very small x, and then it's natural to think that we have to write the Taylor series at x equal a equals 0. Alright, so now we write out the coefficients. F of 0 is as 1. F prime of 0, okay, this term here that we need to substitute 0 into. And then one more, this is f double prime of 0. And this is going to be 3/4. F 第三次微分在0的值，那就是这一个代入 x 等于0。是15/8。Right, 到这里我们已经有了4个系数，从第0次到第3次的4个系数，那我们就可以把这个 f of x 展开来。Right, 所以我们的 f of x 记得是1 over square root of 1 minus x， 就等于它的 Taylor series。那 Taylor series 别忘了这个是 f0 加1。factorial 分之1的 f prime of 0乘 x 减0，我刻意把这个 x 减0写成。Right, so remember the Taylor series. The definition of the Taylor series is this. So the first order term we have to multiply by x minus 0 to the power. We are writing the Taylor series at x equals 0. Okay. Right, so what we have written here, 我们在这里写的是 f 的 Taylor series at x 等于0。那现在把系数带进去之后呢，我们就可以说，我们一个近似的f of x 的一个近似函数呢，就是这个 Taylor 多项式，那就是把后面的项忽略掉的话， 第零次是1 ，OK， the zero order term is 1， and then the first order term coefficient is half times 1 factorial is 1, so x, okay, this becomes x. The next one is 1 half times the second order derivative, that is 3/4 times x squared. And the third term is 3 factorial in the denominator, and that's 6, 1 over 6. 3 factorial 是6。然后呢，这个第三次的系数是15 over 8。OK， 因为我们把后面的都忽略掉了，所以这只是一个近似的函数。整理一下，就是8分之3 x 平。OK， 这个整理一下，3化简剩下286。Alright， 那既然这个是 f 的一个近似函数，那现在呢，那 x 比我们原来问题里面的那个式子啊，也就是说我们刚才探讨了是这个函数的一个展开式。那现在呢，我们把我们的 x 其实要探讨就是 v 平方 over c 平方代入 ，right？ Since we considered v to be much smaller than c, so this is our x which is going to be very small. Then an approximation is f, or rather 1减v 平方 over c 平方根号分之1，其实就等于1加1/2 v 平方 over c 平方加8/3 v 4次 over c 4次再加5。这个是6次 ，right? So I'm just this is the power 6. So now I have an approximation of this 1 over square root term. 现在这个根号分之1的这个式子，我又有一个近似的表达方式。那当然呢，如果我只取这个only first order term， 也就是说我只考虑前面2项，把这个带入到原来的 K 式，就发现 K 式呢，当 v 很小的时候 ，K 式其实是 m0 乘 c square。那这个带进去，1/2 v 平方 over c 平方减1，化简之后，很容易的就看得出，这个就是我们的所谓牛顿物理里面所常见到的1/2 mv 平方的那个这个动能的式子 ，right? So when we consider v to be very small, we can in fact even drop the second and the third order term. If we keep just the first order term and the zero order term, we put this back into the expression of k, then we will find that k in fact is equal to our classical kinetic energy that we encounter in classical physics. 那就是这里也是重复刚才的，所以当 v 非常小的时候呢，我们得到的一个近似的式子 k 的近似式呢，就是我们常见的这个classical definition 呢，牛顿物理里面的这个动能。那这个就表示说，我们本来有一个相当复杂的一个动能函数 ，right？ 这个是本来复杂的动能函数，但是呢，我们把它的 Taylor series 展开之后呢，再考虑说 v 非常小于 c， 所以把后面的项都忽略掉，所以只剩下第一项的话，那就回到了我们 classical physics. Alright, so we started with a rather complicated function for kinetic energy. It's a function of v, but if we express it in terms of its Taylor series expansion, then we truncate it, keeping only the first order term. We find that we recover the classical definition of kinetic energy. 那现在呢，就说，这个近似的方式呢，有没有一个很大的误差？那我们就运用了那个 Taylor's inequality 来判断这个误差的大小。So now we are going to use Taylor's inequality to estimate the error between the two expressions for k. Now remember, the Taylor's inequality is if we find an m that is greater than or equal to the n plus first derivative of f for all x within a certain range, then we know that the remainder is going to be upper bounded by this expression. 这个 Taylor's inequality 说，如果我们找到如此的一个 m， 它是我们的这个第 n 加1次微分的一个上限这个上限有效范围是在某一个范围内的话，那这个 inequality 就告诉我们，这个余数就是误差部分余数呢，也是有这样子的一个上限。所以我们就要找这个 m。那因为我们停在 OK， 刚才我们记得我们停在 f prime right， so we stopped at n equals 1 right， 那个 f prime 而已。所以现在呢，我们就要看 n 加1这个就是 f n 加1微分是2次微分。那我们把2次微分代入，就 n 代入1的话呢，这个是 n 加1的 factorial。那不要忘了，我们这个呢是 x 减 a 绝对值 ，x 减 a 绝对值 n 加1次，但是呢 a 等于0 ，alright， n 等于，so this is we are doing this for the case where n equals 1 and a equals 0. Okay, so we are going to evaluate. We are going to look for this m, then evaluate this expression. 那刚才我们已经见过，第2次微分是这个式子。那现在呢，我们去找它有没有一个上限。那当 v 是小于100的时候，我们把小于100的这个不要忘了这个 x， 这个x 呢，它用了稍微不一样。这个 x 是负 b 平方 over c 平方。那当这个 v 小于100，那不要忘了我们的 c 呢，光速是3乘10的8次，把这个代入之后呢，我们就发现的确有一个上限 m， 这个上限 m 呢，当我们代入刚才这个余数的上限式子的时候，我们就发现这个余数呢会小于这样子一个小数目乘上静止的质量 ，right？ So when we substitute v less than 100, so for example, if you consider v to be the maximum value of v that we are considering is 100 meters per second, and knowing that the speed of light is 3 times 10 to the power 8, if we substitute into this expression, then we find that we do have an upper limit for the second derivative, and this is the value. And if we take this m and put it into the expression for the residue, the remainder, then we find that the remainder is bounded by this very small number times the mass at rest. So the error that we incur by taking the classical physics, the error between that and the relativity is going to be very small. So this is an application of the power polynomial, Taylor polynomial in physics. 所以这个就表示了我们能够在用 Taylor 的这个多项式Taylor 多项式不要忘了，就是 Taylor 展开Taylor 这个级数 Taylor series 砍掉高次项，剩余的变成是一个近似的式子。那我们这里的运用呢，就是说把这个近似的式子呢拿来表达我们原有的函数，这个是原有的函数。但是呢，我们发现它有这样子的一个，这是原有的函数。那现在呢，它有一个近似的式子，我们可以选择丢掉多少项。那现在我们把大部分全丢掉，只剩下的是渐进第1次微分项。结果我们就回到了我们的这个典型的物理。